Hello there. This is hopefully fairly short, quick example on how you can do graphing in Microsoft Excel, as well as to do a linear fit and to find the value and the uncertainty of the resulting fitted slope and intercept. Here I'm using Microsoft Excel 2010. So your screen may look a little different in terms of the layout, especially with the two bars up here, but hopefully the steps will be fairly similar. Of course, the first step here is we are going to enter in data. In this case, I'm using a simple Hooke's law example, so we have force and change in length, as well as the uncertainties, because that will be important when we go and do our error bars. Okay, so let's get a graph going here. To select multiple columns of data, first you select the first column, and then you press Control to select the second column. So just to repeat that, you select the first one first, Control, and select the second one. Then you can go Insert, Scatter, and we want a scatter plot. We can make this a little bigger. Now, Excel is sometimes too smart for its own good. It decided that whatever column we have on the left, that's our x-axis, but since we're doing the Hooke's law graph, we usually want the force to be on our y-axis. To swap them around or to select any new data, you right click on the graph area and go select data. Series 1, you gotta edit it, clean out this stuff and select the correct x data, clean out that stuff and get the correct y data. And okay. So finally we got our forces on the y and our change in length in the x. Legend we don't really need as long as we're only graphing one thing on the graph. Then what do we need? We need error bars. Error bars, they're hidden right now, so the first thing you need to do is to come up with any error bars, and that's under layout, error bar, select any one of these. And once they're exposed, then we can click on it, right click on it, format it to get the right value we want. Most of the time we have custom error bars that we specify, and so this will allow us to select a whole range of data to have a different error bar for different data points. Positive error bar, this is vertical, so it's our delta F. And yeah, that's what happens if you don't clean stuff out before selecting your data. It's an extra stuff in there. Okay, so that's that, and then also for your horizontal, we want to do the same thing. Okay, so fairly quickly we already got our points plotted and our error bars plotted, and our scales are fairly well chosen. So that's the advantage of graphing by computer instead of by hand. To complete the graph, we of course need a title, and personally I prefer a very long descriptive title that tells exactly what's going on, why you're doing the graph, and also a little bit about the method of how you did it. Then we also need axis labels. This bottom here, we need the name, change in length, symbol X, unit M for meters, and also for the other vertical one, force F Newton. So the graph is more or less complete in the sense that we've got title and points with error bars. Next up, of course, is because we know it's a linear relationship and we want to get the spring constant, we need to do a fit. Excel does it all manually for you, and that's if you click on any point, right click, you can go add trend line. And when you add this trend line, you can choose a linear trend line and also display the equation on the chart. Bam! So you can see right away that the relationship is fairly linear. This line, that specified line, does in fact hit through all the error boxes, which is good. And it gives you a certain slope and intercept. So let's keep tabs on it. Intercept. So we'll call this the best fit slope and intercept. Now, the thing on the graph there doesn't always show you enough decimal points, so and a way to expose as many decimal points as you want is to use a slope function. So let me move my mouse away. Equals slope, and then it asks for your y's, comma, asks for your x. Same thing with the intercept. Intercept, y, and x. There you go. You got your best fit, slope, and intercept. To get the uncertainty, the method that we suggest is to draw a worst fit line, meaning a line that is the most different in slope than your best fit line, but still hits all the error boxes. Unfortunately, Excel doesn't have this built in any automatic way, so we're gonna have to draw a line ourselves and pick points off the graph, get the slope manually, like that. To insert a line, you go Insert Shape, this line, and once you have a line, you can adjust it so to make sure it hits all the boxes. So it's missing it, we gotta move up a little bit. That's okay. It's missing this one, so we're gonna move down a little bit. So yeah, you can play with it until you're happy with your actual worst fit line. Now, this has no correspondence with the plot whatsoever, graph, so we need to expose some grid line so we can actually get some points. That's under layout, grid lines. Usually we put both major and minor for both vertical and horizontal. But before we actually read anything off, let's double check that under the axis option, right click on an axis, format axis, that the minor unit is something easy to use. 0.4, that's not bad, but we could change it. We can change it to 0.2. We don't want to change it much smaller because then it gets too busy and we can't read it. On this side it's 0.01. Okay, that's pretty easy to use. So now let's go in and find 2 points where the line hits exactly on the grid line, like here. That's not bad. So that's gonna be 0.24 in the x and 14.2.4. So let's keep these down here. Do a worst fit 0.1. Oops. X-axis, y-axis, 0.24, and y has the 14.4, as we say. Let's double check. Yes. Over here, we have, let's see, this point works pretty well, 0.05 and 2.4. There we go. So then we can work out our worst fit slope. That's of course y2 minus y1 divided by x2 minus x1. And the intercept is we sub in the slope that we have to an existing point. So y minus slope times x. Then the resulting uncertainty from your error bars is going to be the absolute difference between your worst fit and your best fit. And there you go. You got your slope and intercept as well as the uncertainty in the slope and the intercept. With the graph, that's pretty enough that you can print. There's one extra case we have to kind of account for, and that depends on how your data end up looking like. So here I have a separate example. The number is a little different, and the problem with this one is the way the error bars and the data point scatter end up being. I can't actually wiggle this line around from the best fit line very much to get my worst fit line, because if I move it up any little bit, it's going to start missing this point. If I move it down, it's going to start missing this point. So that basically constrains that I have the exact same best fit line as my worst fit line. Does that mean my error is 0? Well, of course not. The points are scattered all around this line, so obviously there's got to be some uncertainty in terms of the slope and the intercept. Fortunately, Excel has a separate way to estimate the error, and it's slightly inferior in the sense that it doesn't account for the error bars, but for situations like this, it gives us an alternative that at least keeps track of the scatter of the points. And here's how you do it. That's equal. Function is line_st for line statistics. Select your y, select your x, and then we have to also put true and true. This function actually outputs up to 10 different pieces of data. We only need the first 4. To get it to show, we have to click on here, select, and then F2. And then we press Control Shift Enter so that it can fill out this 2x2 squares. You notice it gives you the slope and the intercept, and right underneath, these are the uncertainties due to the scatter. So for cases that you can't draw worst fit lines, or if you just can't draw any line that goes through all the error bars, you can use this as an alternative estimate for your uncertainty for slope and intercept.